Hi, and today I'll be talking to you about a problem that is from the AMC12B administration in 2018. And basically what this question asks you is that given you have integers p and q, you want to try to find what is the minimum value of q and at the same time what q minus p is. And why am I showing you this problem today? The reason I'm showing you this problem today is because this is one of those problems where you can actually solve the problem by looking at the answer choices rather than actually having to, try to figure out what p and q are just off the bat, basically. So to start off with this problem, let's first rewrite this problem, all right? So just to make it a little bit simpler, 5/9 is less than p over p plus k less than 4/7. And why am I writing like this? First off, q over here is kind of arbitrary. But from this expression, we know that q has some relation to p because it's basically p plus a constant k. And since we know that q minus p can take on any of these values, 7, 11, 13, 17, or 19th, q minus p can either be any of those values, 7, 11, 13, then we know q has to take on a value of p plus 7, 11, 13, and ... And this value, we're just going to call our constant k. So now in this problem, I actually claim that by minimizing q minus p, you're also able to minimize your value of q as well, given the answer choices. And now we'll see why this is the case in this problem. It may not sound entirely, correct or all, but this is one of those problems where you can kind of see a relation between these, between q and p and q, just based off of trying to do some basic simple algebraic manipulation from this expression. So let's first separate this expression into two expressions. 5/9 is less than p over p plus k, and p over p plus k is less than 4/7. And over here, we're trying to solve for k to see, what this q minus p value should be, to be able to satisfy the fact that p and q have to be both positive integers. So we find from here that 5 times p plus k is less than 9p, and we find out over here that 7p is less than 4p plus k. And from this expression, you move the 5p to this side, and you get 4p is less than 5k. And from this expression, you get that 7p is less than, or 3p is less than 4k by moving the 4 over here and subtracting and doing the addition and doing the arithmetic. From these two expressions, we're able to find out that k is bounded between 4 over 5p as well as 4/3, should be 3/4 p. So it's bounded between these two values. And what this tells us is that this k value that we initially said could take on any of these values, 7, 11, 13, 17, or 19, has to satisfy the fact that there exists an integer p that will be able to, satisfy this inequality. So that way, if we can find a k that basically allows a p to exist, then q can easily exist because we know that q is basically just p plus k. And if p and k are both integers, then q definitely will exist. So this is why I said, so going back to my claim before, that I said if we minimize q minus p, we're also kind of being able to minimize q. And the reason for that is that q minus p over here, as I said, was k. I just said that k would just be q minus p. So if we minimize the value of k, then we're also able to kind of minimize the value of p, because the larger k is, the larger the p has to be able to satisfy this condition. And q is based off of the addition of p and k. So if k increases and p also increases, then q will also increase. So we want to try to get a minimum value of k as possible. So to start off, let's first test with 7, So k is equal to 7 is less than 3/4 p, and it's less than 4/5 p. So breaking down this equation, we get p is less than or 3/4 p is less than 7, and we also get 4/5 p is greater than 7. From these two equations, we get p is less than 7 times 4/3. P is greater than 7 times 5/4. That's basically multiplying both sides by 5/4, multiplying both sides of these by 4/3, and we get p is less than 28/3, and p is greater than 35/4. To get this value, 28/3, we get 9 1/3. For 35/4, we get 8 3/4. And which value of p satisfies these values? We can clearly see that the value of p that satisfies this value is basically 9. 9 is less than 9 1/3, and 9 is definitely greater than 8 3/4. So we've gotten that p is equal to 9. And we know, of course, that q is equal to 7th because we know that k is equal to 7th because that's the value we plugged in over here for k. So since p is equal to 9, k is equal to 7, then that means q is equal to 16th. And although the question is only asking us what p minus q is, and q minus p is, and we know that q minus p in here we just set as k. So basically our answer is going to be 7th. And to verify that our solution is in fact correct, let's plug in basically our values of p and q into this equation. We got p is equal to 9th and k is equal to 7th, so that means q is equal to p plus k, which is equal to 16th. So plugging in 5/9 is less than 9/16 is less than 4/7. We first solve this part of the equation, and we get that 5 times 16 is less than 9 times 9. And we, in fact, do get that 80 is less than 81, so it's a check mark. Let's now look at this part of the equality. As you know, we'll just multiply 7 over here, 16 over here, so we get 9 times 7 cross multiplying. 9 times 7 is less than 4/16, and 63 is less than 64, correct. And obviously, as we've seen, we've shown that this is also the smallest solution for q, because q, as we said previously, depends on both p and k, and basically the larger our value k is over here, then the larger p has to be able to satisfy the bound over here. So if k is, let's say, 1, then p might be between maybe something somewhere between 1 and 2, whereas if maybe k was 100 or something, p would definitely have to be much larger to make the maximum bound and the minimum bounds both enclose the value of k. So as we can see, we chose the minimum value of k that basically allowed for the minimum value of p and also the minimum value of q, and especially the minimum value of q over here. So that is our answer.